Hello, this is the start of the ADC tutorials. At this part, we will get some introduction into the STM32 ADC, and then we'll implement the single channel conversion mode at this particular video, and then we'll do the other modes into following videos. So to start off, the ADC on the STM has generally the following hardware structure, where we have here on the left hand side at the bottom, we have some multiplexer for channel selection, we have injected and regular channels, and then we have some regular data register and injected registers. We have the analog watchdog, end of conversion interrupt, and some data transfer through memory, such as using DMA or something like that. So that's generally the hardware structure of an STM ADC. And now the normal working principle of such ADC type, it's the SAR type, which should scan for all quantization levels. The SAR type on the STM boards, there are some with 6 bits, which take 6 clock cycles, 8 bits, 10 bits, and 12 bits. Our starter kit, the STM32F1 Bluebill board, the one we're using, only has a single configuration. It can only work on 12 bits mode. So that's what we'll be programming. So generally, this type of ADC work on the principle of sample and hold circuit, and it has an internal DAC. So it compares the output of its DAC with the sample and hold circuit result. And when they kind of match closely, then we take that as a converted value. And this is the trick. This is the clever bit. This will determine the sampling rate and the total conversion time of the ADC. So here is some very simple formula here down at the bottom, where we calculate the exact conversion time of the ADC. This is important in some periodic application where it is very critical and important to know the sampling rate and the kind of maximum sampling speed that you can get. So this can be calculated by the number of bits plus the number of cycles for the sample and hold circuit. And now obviously the sample and hold circuit is consists of some sort of capacitor charging with the input voltage. If these cycles are very small, then you might not get very accurate ADC reading. So it's important to have reasonably good number of sample and hold cycles. And that will eventually determine the maximum sampling time. So here we have an example. If we have a 12-bit resolution, like the one we have with the STM-F1 board, and we have selected 28 sample and hold cycles, and if our clock is 21 megahertz, this is an example, then the ADC conversion time would be 12 plus 28 divided by 21. That will be 1.9 microsecond. And in our case, however, we know that our ADC clock speed is, we have a prescaler, if you can recall, is 12 megahertz. This is our ADC clock on the STM-F1. So that number will be divided by 12. Those are the exact settings on the STM board. Alright, so this is the working principle. I don't want to spend lots of time getting you bored by the principle. Let's get into coding, and I'll show you how these kind of things are configured as parameters. These are some details on the kind of things you need to do, but I always like to start coding, so let's do that, and then later on we can perhaps get back at this and try to relate. But that's will be relatively easy when you see that on the code. So let me show you how that looks like. At this video, we will program only the single conversion mode, where we are going to select a channel and have it converted. In our hardware kit, we have 3 normal analog inputs. We have the potentiometer, we have the potentiometer, and we have 2-axis joystick. So this one with an X and Y. This is the potentiometer, and those are connected to PA1 for the potentiometer, PA2 I think for the X-axis of the joystick, and then PA3 for both the Y-axis and the microphone. We will connect the microphone later on in perhaps another training course with the HAL library to record from the microphone and store in an SD card. But for this tutorial, we will be using the potentiometer and the joysticks only. Alright, so potentiometer on PA1, the X-axis is on PA2 pin, and PA3 for the Y-axis of the joystick. So we have 3 channels, and in this tutorial I'll give you the option to switch between these 3 in a single conversion mode. Alright, so the first thing we need to do is to create an ADC header and source file, just like what we did for the rest of them. So I'm going to navigate to peripherals, header. I will add an adc.h, and on the source folder I will add adc.c. Okay, and let me close the unnecessarily opened tabs. So I'll open everything that I think it's unnecessary. All right, excellent. So the first thing we want to do in the ADC is there is a very useful. The first thing is to set the ADC GPIO pins. So at the very beginning, we want to include main.h as usual to get our STM header files included too. So the first function I am going to define is to configure the ADC GPIO pins. So ADC GPIO pins, and those are PA1 for the potentiometer, PA2 for joystick X, and PA3 for joystick Y. So this is joystick X, and this is the potentiometer. All right, so we want to configure those pins as analog inputs. All right, and I will call the function ADC as a prefix, and I'll just say GPIO config. Okay, now let's take a look at the reference manual. Now heading to the source file first, where we need to define the ADC header, and now we're going to write the function definition of that GPIO configuration. And now, according to the reference manual, if we would go to the GPIO configuration section, this is PA1, 2, and 3, so they will be in the low configuration register. In order to set a pin in analog mode, it needs to be input, and this one needs to be analog. So we need to clear both the CNF and the mode bit field for our pins, pin 1, 2, and 3. And that's relatively simple. So let's do that. And before we do that, we of course need to enable port A clock, since all these pins are on port A. And I might as well just copy port A enable from one of my GPIO configuration functions. Okay, here we go. Now let's do PA1, and then PA2 and PA3 configurations, and those would have we need to go to the control register low. We need to clear some bit fields, so we use the clear operator, and GPIO CRL mode. Okay, if we don't see them, then we can always do kind of save. Perhaps that will rescue it, yeah. So I'm interested in mode number 1. I want to clear that fully, and also the CNF 1. Okay, so that's the CNF bit fields. This one would determine that it's an input mode, and the CNF clearing would make it analog mode. Alright, so we need to apply exactly the same thing for the other pins, PA2 and PA3. So we need to change the number to 2 and 3 for this one. And that's it. So this would be the entire GPIO configuration. And then the next thing we need to do is to configure the actual ADC peripheral. And that's where the fun starts. At this part, you will start to see and understand how ADC work in register level. So I'm very excited to show you that. Now, this is the main function of this tutorial, perhaps. So I'll call this function single config to configure the selected pin. Now I can do some, I'll leave it void for now, but then I can add the functionality to select channel. For now, I can, yeah, I can keep it like this, I guess. Okay, now I'm going to start defining that function body. Okay, so in the definition of this, we need to enable our ADC, ADC1, and this MCU only has a single ADC. So that's part of APP2, I think. So it's very similar to where we enable port A, but we're going to select ADC. Here we go, ADC1, yep. We don't have ADC2, I think. So that's just generally appeared because this is the B series. Okay. So we enable ADC clock. Now let me take you to the ADC registers to get you appreciate what goes on in the background. Now let's study the ADC registers very briefly. Okay, so this is the reference manual, and here are our analog section registers. Let's navigate to the ADC registers. We have a status register, which will come useful when checking for conversion result. If it's done or not, we read for the end of conversion flag. And we have control register 1 to do some analog watchdog, interrupt, scan mode, all these kind of stuff, which we might actually not need for this part of the tutorial. These more of advanced settings, we might just need to leave them as default. Now CR2 is an interesting one because this one allows us to select, to turn the ADC on, to select whether we want continuous or single mode, to actually apply some calibration and to set the alignment and generate a software restart. So I think we'll be using control register 2 a lot at this tutorial. And then we have the sample time register. This is for channel 10 to 17. We're not going to use that. This is 0 to 9. Yes, I think we'll use this register to set the number of sample and hold cycles that I talked to you about in our slides. So this will determine this number of sample and hold cycles. We'll be using this register, I believe. And then we have, this is the injected. This tutorial is not about injected channel, not about analog watchdog. We have the SQR. This is to select the ADC regular channel sequence for channel 13 to 16. No. Channel 7, no. This is channel 1 to 6. I think, yes, we'll be using that because we have channel 1. We have just a single conversion, so that's sequence number 1 that we are going to program, I believe. Yeah, so that's it. These are the registers I think we're going to write some coding into. Okay, so let's begin with control register 2 settings, and I'll list the configuration we need to do. So we need to ensure we do right align, single conversion. So that's by disabling the continuous mode. We need to select software trigger as the trigger mode, because we're not going to have any external or timer. We just want the software to start ADC whenever is necessary. Yeah, one thing we will do as well, we want to set the sample time to 28 cycles. So this would result into, we know that the resolution is always 12 bits plus 28 divided by 12 megahertz because of our ADC timer that's set up in the RCC clock. So our ADC prescaler is 6, and that would result into 12 megahertz clock speed. So that would result into 3.3 microsecond. If you get the calculator out, that should be the result. And we want to set rank 1 in the sequence register as one of the channels that we select, either channel 1, 2, or 3. And then, because we have PA1, PA2, and PA3, we can select one of them. Okay, and then the power up, we need to power up the ADC. And then wait for the ADC to stabilize. This is relatively simple if you're familiar with STM ADC's register level. So bear with me a few minutes, you'll get to see all that in a moment. So the first one, right align, is configured in control register number 2, which is the align bit. And according to the description, if you clear that, you'll have right alignment. So let's clear that bit field. So ADC 1, control register 2, and I want to clear that bit field number 11, or I can rely on the SIMSYS definition. So ADC CR2 align, and I want to clear that bit field. So that's it. I expect that to be 1 shifted by 11. Exactly. And now for single conversion mode, I need to clear continuous mode bit field, which is this one. So I need to clear that. I am going to use the same clear method, but I am going to clear the continuous bit this time. And also I need to select software trigger to be the software timer, and that's selected also in ADC control register 2 as part of the external selection fields. According to that, if we write all ones, that means we want software start. So that's what I'll do. Let's just copy this to make it quick. I am setting field, not resetting, so I'll use the OR sign only. And I am setting all those external selection thing. So that should be 7 shifted by 17. Exactly, that's good. And then we want to select our sample time cycles. I think we're done with control register 2. Sample time cycle is in sample register number 2 for channel 1, 2, or 3. So we need to do one for one of them. And the safest option is to, yeah, this is for sample for channel number. I can do that for all the channels that I have to be on the safe side. Okay, so let me do that. So I need to write 1, 1 into there. So 1, 1, 0 to have 28.5. That's actually 28.5 cycle, not 28 purely. All right, and we can write that to 1, 2, and 3. These are for the number, for the channel number. Okay, so let's do that. And I'll do that for PA1, PA2, and PA3 to be on the safe side, because I can use, I haven't selected which one of them, so I need to select one of them later on. Okay, so that would be ADC1, the sample register number 2, and I want to first clear those bit fields that I don't need. Well, I need to clear the bit fields so that I can set them correctly and ensure the setting went through. So I want to clear bit field for 2, and that would be number 1 for now. Yes, I want to clear them up and then set bit number 1 and 2. So bit 0 and bit 1. So that would be 0, and then OR with 1, but that's not going to be clear anymore. That will be set. So I need to put the OR sign. So what this does is that it's first going to clear all the bit fields that are associated with this one, and then set them up to this. So bit 0 and 1 need to be high, and that's what this one is for. Okay, and we need to do the same thing for BA2. So that would be 2, 2, and 2 in here. We do the same for BA3. I know this is only single channel, so we'll be using only one of the channels, but I will select either channel 1, 2, or 3. If I set them up all together, then I'm on the safe side. Okay, now we need to select the rank, so which channel we want to convert, and that's on the ADC SQR3, I believe. Yep. So if you write, we first need to determine the number of conversion, which we would write into the L field of ADC SQR1. By default, this is set to 0, but we can verify, we can make sure that it's set to 0. So before that, need to do number of conversion to 1 only. Okay, and that's done through ADC SQR1 register. And for that, we need to clear some bit fields. So we do the clear operation, and that's ADC SQR1 and the L bit fields, exactly. So I need to clear all of them up, and if that's correct, that should be F shifted by 20. Is that right? Yeah, that's correct. Now, for the rank, that will imply some channel selection, which is ADC1, SQR3 this time, and we need to write something in there. So since we only have a single one conversion, so whatever you write in here, if you write to the first sequence, if you write all zeros, that will be channel 0. If you write 1, that will be channel 1, and so on. So we need to specify our channel. Well, one easy way to do that is to define some enum and have 1, 2, and 3, and have the user pass them. So I can go to the adc.h and define some enum, like type diff enum, let's say ADC single channel select, and I want to define a type diff enum. I would say ADC single select, a tag, because this is not the name, this is just a tag, and this would be the type diff name. And I'll use the exact name. This is just a naming convention. I would say potentiometer. This is channel 1. This is equal to 1. And then the others would follow. So I don't need to write 1. It will be 2. So this is joystick X. And then we will have joystick Y, and also the mic. They're all together into a shared bin, but this is only the Y in my case, so I'll just leave it the joystick Y. Okay, so that will be 1, this is 2, and this is 3. And I can pass this as a parameter to the function. So the single conversion, I'd say channel, and that would also need to change in the source file. So this is to select which channel you want to convert, since we only can convert one channel at this particular mode. All right, so we have channel as a parameter. I'm going to pass it in here. So 1, 2, or 3. Really simple, huh? Really good, huh? Okay. Now, after that, we need to power up the ADC, as we said. In order to power up the ADC, there's a control register number 2 bit field number 0, which says ADC on. Okay, so we need to set that first bit field to 1, so that will be ADC CR2 and ADC on bit. And after that, we need to wait for it to stabilize, and that usually takes on a few cycles according to the datasheet. So we can wait for 1 microsecond or something like that. I will estimate that it would be I equal to 0. I will wait 36 cycles, and since I am on the single for loop takes about 4 cycles, and I know my clock is 72 megahertz, so 4 cycles times 36, 144, 72 megahertz divided by 144 is 0.5, so that would be roughly 1 or 2 microseconds, something like that. So this is just doing a few wait to a couple of microseconds. So that will be 2 microseconds. We're going to wait for the ADC to stabilize. Okay. And then after that, we have configured the ADC. Now we need to, there are a couple of things we need to do. We need to start the ADC and stop it. So if you want to start conversion, and there's a function called poll for end of conversion. So we want to check if the conversion is ready or not. So let me do the start and stop. So this is ADC start, since we have selected the software start mode. So we need to start it ourselves in software. So I just say ADC start and then ADC stop. Okay. We're getting there. This tutorial might be slow, but I really like to go slowly so that you can see all the detail. And that's the whole point of having a training as opposed to very fast tutorial. Okay, so let's do the start and stop functions really quick, and then we're going to come to our poll function. Okay, so for the ADC start function, we first need to clear the status register. This is a common good practice to ensure this start is not affected by previous status. And then we need to generate a soft start according to control register number 2. Let me show you that. We can generate a software start by writing to bit field 22. Okay, let's do that. Okay, and if I can recall, on page 218, there is a suggestion to also set ADC AD on. So conversion start when AD on bit is set for a second time by software after ADC power up time and time stabilize. So we need to set that bit again high to start ADC conversion. So we need to do that for ADC on. So that's 1 shifted by 0 in that register. Or if you like, we can do the SEMSYS definitions. So that's it for the ADC software start function. And now for stop, it's really as simple as reversing the operation. So we will do the status register okay, but the ADC software start, we will clear that up. It's really that simple, and we don't need to do anything with the ADC on. We can leave the ADC on, but it's not going to start a sequence or anything like that. Okay, so that's it for those. And now we've got 2 more functions to go. We need to check if the conversion is done or not, because we don't have an interrupt mode at this part of the tutorial. So this one should say pull for end of conversion. And this function would take the form of returning a Boolean variable, and then I can say pull for end of conversion. Okay, and this takes a timeout, of course. We don't want to wait indefinitely in case something wrong happens. Okay, so pull for end of conversion, and also let me write the prototype for ADC read value. So once we have got the value converted successfully, we want to acquire that value and read it in 12 bits format, which will be the ultimate fun moment indeed. So that returns an unsigned 16, an ADC. It will be only 12 bits, but this is the smallest standard variable type we can use. Okay, so ADC read value. This takes no parameter and it only return a value for us. So let's go in the source file and define what those functions are. Now, for pull of end of conversion, we first need to get the initial tick for the timeout. So we would say start ticks equal to rcc ms get ticks. So this is to get us the initial ticks so that we can use it for our timeout. And then we will wait until the status register have the end of conversion flag set. So we will do while, and we'll wait while ADC 1 status register, and all that we want to make an AND with 0x02, because that's the end of conversion flag. And if this one is 0, we want to carry on in our loop. So while this one is still 0, we continue into the loop and now keep track of the timeout. So we would keep track of our timeout this way. If the current ticks minus the initial ticks exceeded our timeout, then we know we have a timeout condition. I'm just going to put brackets. So if this one is bigger than my ms timeout, then I know that I've exceeded the time allocated for me, so I'd return false. Otherwise, if we exited the while loop successfully, if the SR equal to 1, the end of conversion, then I return 1, and I know that my conversion is ready. So that's it. This is as simple as this. Now for the best function of them all, because that will be the last one, is to read the ADC value. So for that, we are going to return whatever ADC data register is, and then we'll have that. We end this with the 0xFFF to ensure it only takes the 12 bits. It would already do that for us, but this is just to be on the safe side. And what we're doing here, we're reading the data register. This is the register for returning the ADC converted value under regular channel. All right, we have done writing all those functions. Now it's time to actually test them. So let's do that. This is really fun. We're going to go to the main, and we are going to include ADC. .h. I can just get rid of the interrupt thing. I don't need it anymore. I will just delete it to make my code cleaner. Yeah, this one gonna go as well. Let's just make this 1 second. Okay, so the first function we want to call is ADC GBIO config. We'll call it at the very beginning. Let's do ADC. And then we need to do the single channel conversion. So we need to do this particular one. Okay, we need to select the channel. So let's do the potentiometer first. According to my parameter, this should work fine. And that's it. Now we can start reading ADC. So I'm going to define a variable for my ADC value. I'd say ADC value equal to 0 initially. And what I'll do is that in here I will, let's make this smaller so that I get fast conversion. And perhaps it's time to get rid of this printf hello world. And I want this while loop to be fully for my ADC. So the first step is that I want to start the ADC and then wait for end of conversion. So that's where pull of conversion comes in useful. I'll wait up to, let's say, 5 milliseconds. It shouldn't really take that long. It should be very quick. So if that's successful, I'm going to read the ADC value. So I'm going to read whatever into the ADC register using the read value function. Okay. And I can actually print something, say ADC read successfully. Right, that's exciting. Otherwise, I can do, in case this timed out, I know, so I'm gonna print ADC failed or timed out, whatever you like. And then at the output, I can, outside these conditional statements, I can just print the ADC value purely. So I would say ADC value is equal to, and that will be an unsigned integer thing, or it could be just D. And then I typecast to integer because of this printf thing. It will throw me a warning, and it will be my ADC value. I think that's everything. So are you ready to test that code? I'm very excited. Now I can do an LED toggle. I always like to have LED toggling in the background to just make me, I'll feel comfortable to see the LED blinking. It indicates everything is working. Okay, let's choose the green again. And that's it. That's really it. This is a single conversion mode. Let's compile the code, load it to the board, and hopefully that's gonna work really well. Okay. Awesome, we've got no errors. Let's put our board into boot mode. Okay, let's open our flash loader. And comport 14, that's brilliant. Download to the device, and I need to select the hex file. There we go. All right, let's have a look. Right, that's good. I can see the green LED. That makes me really happy. Now let's see the conversion. Oh, that's nice. So ADC converted successfully, and it's reading 400. Now let me play with the potentiometer then. I'll make this one slightly bigger too. Okay, so I'll play around with the potentiometer. I move it to the left. It goes to 0. That's the end. Now I move it to the right. It goes up to 4096, I expect. Yeah, pretty much. There we go. So this is working. That's amazing. And now I can also change the channel. I can do the joystick x-axis if I like. So let me do that quick before I end this tutorial up. So I'll select the joystick x-axis and I'll recompile and put the device into boot mode again. Let's get the flash loader back again. There we go. Let me select the hex file just to, in case it's not selected, and flash that again. And that's pretty nice. Let me open the comport, and that's now reading hopefully from the joystick. Let me play around with it. I'm not sure which one is the x-axis, so I'd have to play around. There we go. So that's the x-axis. You move it forward and backward, and the values do get changed. That's pretty cool. That's very nice. All right, so that brings me to the end of this video. Thank you.